This webcast talks about some of the vector math that we will need in order to handle forces that are acting in different directions. So a vector is a quantity that has both a magnitude and a direction. For example, you could talk about a displacement of 15 meters due north. 15 meters is the amount or the magnitude of the displacement, and due north is the direction. We have already talked about a number of vector quantities, including displacement, velocity, and acceleration, and soon we're going to also talk about forces, which are also vectors. The opposite of a vector is a scalar. A scalar is a quantity that only describes an amount of something. For example, elapsed time, the amount of money in your wallet, temperature. These are all things that can be described as a quantity, but they have no sense of direction. Typically, vectors are represented as arrows. The pointed end of the vector shows the direction that the vector is acting in, and if you're careful, the length of the arrow is proportional to the magnitude of the vector. So there are a couple of methods of describing vectors, and we're going to talk about both of them, and we will use both of them interchangeably. One method is called polar notation. So in polar notation, a vector is defined by giving its magnitude and the angle in standard position that indicates its direction. And so the vector would equal, and you would put in parentheses, first the magnitude and second the angle in standard position. So you would need to put units on both of these quantities because they would be different amounts, right? If this were a velocity vector, the magnitude would be in units of meters per second, and the angle would be probably in degrees. It could also be in radians, but usually we use degrees. All of the angles that must be defined in standard position. So if you recall from Algebra 2, standard position is when the vertex is placed at the origin and the angular rotation begins on the positive x-axis. So you rotate around counterclockwise until you bump into the vector that you're talking about. That angle is the angle that we would put in these parentheses. Here's an example. A car is going at a speed of 5 meters per second in a direction 30 degrees west of north. So on a coordinate axis, we typically would say that east is to the right, west is to the left, north is straight up, and south is straight down. So in this case, they're talking about 30 degrees west of north, which means that you start looking north and then you move 30 degrees west. But that 30 degrees is not the angle in standard position. For it to be in standard position, we have to start on the positive x-axis and then rotate counterclockwise until we bump into the angle, into the vector. And so we're moving 90 degrees as we go from east to north, and then we go another 30 degrees. So the angle in standard position for this vector is 120 degrees. So in polar notation, we would say the velocity of this car is 5 meters per second, 120 degrees. That tells us how fast it's going and in what direction it's moving. In polar notation, the magnitude is always positive. There would be no meaning to putting a negative magnitude. Always use the angle to show the direction of the vector. let's practice a couple. Let's see here. So I'm in worksheet 4B, and I have some 1/2 centimeter grid graph paper here, and let's just draw a few vectors. So first I'm going to draw a vector that is 5 centimeters long and points to the right. I'm going to call that delta x1. So if I start it right here, since each square on this paper is 1/2 centimeter and I want this to be 5 centimeters long, I'm going to make it 10 squares long, and it's pointing to the right. So the magnitude of this displacement vector is 5 centimeters. The angle would be, if I assume that I have put the vertex here at the origin, and then I start at the positive x-axis and rotate until I bump into my vector, I don't have to travel anywhere at all, right? This vector is sitting on top of the positive x-axis. Therefore, the angle here is 0 degrees. What if, let me draw another displacement vector. This one is going to be 5 centimeters long, but it points to the left. So the length of this vector is the same. So the magnitude is the same. It's 5 centimeters. But what is the angle here? So again, I would think about putting the vertex at the origin, and I have to rotate starting at the positive x-axis until I run around and bump into the vector I'm looking at. So in this case, I have to go half of a circle, or 180 degrees. And so here the angle would be 180 degrees. So in polar notation, the angle is telling me the direction that it points. Both of these vectors were the same magnitude. They were the same length of vector, but their angles were very different. Okay. There's another way of expressing a vector, which is called rectangular notation. And in a rectangular notation, the vector is expressed by giving the extent in the x direction and the extent in the y direction. And you put those numbers in parentheses. Here, both of these units, or both of these quantities, Vx and Vy, probably have the same units. So you could put the units either inside these parentheses or outside. Here's an example. So a car travels 8 kilometers east and 4 kilometers south. And so it was displaced in a way that's shown by this red arrow. That red arrow is a vector, and it could be expressed in rectangular coordinates as 8, -4 kilometers. Remember that east is to the right, west is to the left, north is straight up on the y-axis, and south is straight down on the y-axis. So east is taken to be a positive direction. West and south are taken to be negative directions. Okay, so let's go back to and draw a couple of vectors that are and just compare the differences between them. So let's see. Let me say that there is a displacement vector that is 3, 4 centimeters. And maybe I have another displacement vector which is 4, 3 centimeters. Let's draw them and see if they're the same vector or different. Okay, and you can just choose any place to start your vector. So I'm going to start mine right here, x3. And so it has to go 3 centimeters to the right, because the extent in the x direction is 3, and it has to go 4 centimeters in the y direction. And so this is that vector. And so just so you can see, it went 3 centimeters in the x direction, and it went 4 centimeters in the y direction. And so you can see it's pointing up and to the right. What if I drew 4, 3? So then, and let's see, I'll just start it right here. It has to go 1, 2, 3, 4 in the x direction, and 1, 2, 3 in the y direction. This is delta x4. So they are not really pointing in the same direction, right? This one went 4 centimeters in the x direction and 3 centimeters in the y direction, so they are not quite the same thing. They're not pointing in the same direction. Could I express these in polar notation? Sure. So let's see that. So I need to know the angle in standard position. That means that I assume my vertex is at the origin, and I go from the positive x-axis over to the vector. And over here I'd put my vertex at the origin and I'd go. So they're at slightly different angles. Let's see what these are. So for delta x3, that angle, theta 3, is the arctan of the opposite over adjacent side. So let's see what that is, which is 53.13 degrees. And the angle for theta 4 is the arctan of opposite over adjacent 3 over 4. Which is 36 degrees. So if I wanted to describe these in polar notation, I would give the magnitude of them. Oh, maybe I should find the magnitude. What is the magnitude here? If I use the Pythagorean theorem, this is the square root of 3 squared plus 4 squared. So that would be 5. And this one would be the square root of 3 squared plus 4 squared. Okay, so they have the same magnitude. They both are 5 centimeters long, but they're at different angles. So in polar notation, x3 would be 5 centimeters at an angle of 53.13 degrees, and x4 would be 5 centimeters, but it would be at an angle of 36.87 degrees.